All right, we're here to talk about question H6, a differential equation question with a slope field. So let's get started. First thing you do, you read the question and you realize what we're given. We're given a differential equation and an initial condition. All of this here, well, there's a limitation on the differential equation, and that's just giving us a name. This is the solution right here, this y equals f of x. They're calling y equal to f of x. This function, that's the solution, or the solution to this differential equation subject to that initial condition. Okay, now, if you're not totally familiar with that vocabulary, you're still okay for part A, at least. They want the slope of the line tangent to the graph at a point, the graph of f. So what do you need? We need the slope. How do you find the slope? It's a derivative. How do I find the derivative of f? Well, they gave it to you. This is the derivative right here of f. That's what that notation means because y is equal to f. So all we need to do is plug in this point 1, 2 into this equation right here. Notice there's an x and a y variable on this equation. That'll give us the slope. That's what they do. That's worth 1 point. That's nice notation. That's the derivative of y with respect to x when x and y equal 1, 2. All right. Part B is the slope field. So what do you need for the slope field? Well, they gave us these points to fill in. So we know what points we need. We take the x and, for instance, for that point, we'll take the x and the y coordinate of that point, and we'll plug them in to here into the differential equation, and that will give us the slope of y at this point right here, and the slope of y at that point is the slope that we want, so we draw a little line segment through that point that has the slope that we just computed. Here's what the slope field looks like, and here's an example, two examples of two different points. So I picked out point 1, 1, and just to show you, so at 1, 1, we plug x equal 1 and y equal 1 into the differential equation, and this is my work, and you get 0. You should test that out. You've got a few of these points to compute. So the slope of y, which is f of x, at 0, at 1, 1, is 0, and you can see they drew a horizontal line segment, a line segment with a slope of 0 there. Here's another example at 2, 2, this one right here. Well, we plug x equal 2 and y equal 2 into the same differential equation. Here's my work, and you get dy dx is equal to 1/2. So this line segment at 2, 2 needs to have a slope of positive 1/2, and that's, a reasonably drawn line segment with a slope of 1/2. And so you proceed. You have, what do you have? 1, 2, 3, 4, 5, 6. You have 9 of these to do. That's all it is. It's not anything fancy, but it's, a little bit of a grind. But at least that is a pretty easy grind. Then comes part C. Part C is the solving the differential equation part, and that's worth most of the points. You'll notice part A and part B together are only worth 3 points, so that means part C is worth 6 points. What you have to do is solve this differential equation symbolically subject to that initial condition. So here's what I tell my students about solving a differential equation. You have to separate and then integrate, and then you can celebrate, but you can't celebrate without a C. So it's a little hokey, but let's look at what happens. Well, first of all, you know what? Let's look at the scoring first. So there's our 6 points. Big penalties. If you don't use a constant, you're only eligible for the first 3 points, and then after that, it doesn't matter what you do. You're not getting any more points. So the constant doesn't seem like a big deal, but it really is. Make sure after you integrate, you add a constant to one side. You don't have to add it to both, but you do have to add it to one of the sides. Also, if you can't separate the variables, you get penalized greatly. So here's the solution. Here's what they do. There's the differential equation. Here it is. They did two things at once here. They both separated it. Now, how do you separate this thing? We need to get all of the x and dx stuff on one side and all of the y and dy stuff on the other. In addition, the dy, that differential, and the dx have to be factors of their respective sides. That means since dy is on the top of this side, all the y stuff has to go to the left. So that's what they did. They divided both sides by y minus 1. That's the only factor that has y in it. And then they sort of multiply. It's not really multiplying, but it looks like it. Both sides by dx. That ships the dx over to the right side. And so now, without the integral signs, this equation right here is a separated differential equation. And now you just draw the integral sign, you take the integral of each side, they combine those two steps. Now, of course, I need to find the antiderivative of each side. This side right here, the antiderivative of, well, if you want to use a u substitution and think of y minus 1 being u, you can, but then du dx is 1, so du equals dx. However you do it, the antiderivative of the left side is ln, absolute value of y minus 1. And then the antiderivative of this side you can do term by term using the power rule, and you get that. Here's the c. Don't forget that c. You could have put the c on either side, but you usually like to attach c to the x side because we're going to be solving this for y. Remember, the solution to a differential equation is a function, and the solution to this one is, they told us y equals f of x, so we're solving for y eventually. Now, once we have this, we use the initial condition. So now it's time to find the numeric value of c. Use the initial condition, which is 1, 2. That's from above. So you put in 2 in for y and 1 in for x, and c then is the only variable, and you get c equal -3. So true to its name, that's a constant that doesn't change. So c is equal to -3. I replace that c with -3, and then I kind of start over now with my variables x and y. That's right here. So now it's time to start thinking about, well, let's see, how do I solve that for y? Well, the big thing, this is kind of complicated, or a little, they added a little complicating factor with that absolute value. But if you notice, at this point, 1, 2, when y is 2, this part right here, the argument of the absolute value, the inside, is positive. So since this is positive at 2, I know that the absolute value doesn't do anything for any point that's on the solution curve. So I can blow off the absolute value. I can make it just a set of parentheses because I know now that y minus 1 has always got to be positive for this particular solution. So after I know that, how do I get rid of ln? Well, e to the both sides. And then once I e to the both sides, I'll have y minus 1 equals e to this monster. And then I just add 1 to both sides, and I've got y on its own. So this is the solution. This is the what we would call the particular solution. It's the solution of the differential equation subject to the initial condition. It's the curve that conforms to this slope field and goes through the point 1 comma 2, this one right here. So I don't know what it looks like. It may look something like that, and then um, maybe, I don't know. It's, well, that didn't draw it very well. All right, so again, let's look at the points. What do you have to do to this? You have to separate it and integrate it. They did it in two, they did both of those steps in one. So, well, actually, they separated it and they wrote the integral signs. So they get a point for this, they get 2 points for that, and then that's it if you forget the constant. Don't forget the constant. You get a point for getting the constant, and then that's sort of using the initial condition. I guess you get, I don't know. I don't know the difference between these 2 points actually. And then you get a point for solving for y. So it's 6 big points. I think if you know how to do this, and I think, certainly with a little bit more practice we will, um, this can be a pretty quick uh, point scoop. So I kind of think there might be a differential equation on there. Let's make sure we know how to do them. Perfect. Thanks.